So there's a lot of different areas where sensors can play a role, and the nice thing is you don't have to get to some dreamland of making fault tolerant thresholds. Like even sometimes factors of 10, even factors of 5 can make a big difference for industry. So for example, in mining, companies like BHP Billiton, they look for diamond mines, and basically they use gravimeters to do this. You look at, you can stick a gravimeter on a small plane, and then just fly the plane over a region of Earth, and you look for density fluctuations based upon variations of the gravitational field. And from that, you can say, okay, this is a good spot to mine. And it saves a lot of time. It also is much better for the environment. You can do other things like look for aquifers, or look for cavities, which could be used for carbon sequestration. So there's a lot of things where just having a small but important factor improvement in the precision makes a big difference. So some big areas where this is true are gravimetry, measuring the gravitational field, inertial sensing for navigation. This is for aircraft or for submarines, and frequency standards for clocks. We're in cases where you might have GPS denied environments and you want to know where you are. You need to have very good clocks. It goes back to the old problem of wanting to know what longitude you're at, and being able to sensitively measure electromagnetic fields for like high precision advanced material technologies. You really want to know whether your device is going to work, so you need to know whether the electric fields are going to be beyond some threshold. And in medicine, there's being able to have in situ measurements of reactions happening in cells. So all these things can benefit from small but significantly enough improvements in precision. And quantum materials can provide that essentially using entanglement, which is not at all possible with classical systems, as we know. So yeah, I think there's a lot of opportunity in industry to absorb these quantum technologies fairly early on, or at least in the midterm. The two areas I've been looking at are using what is called magnetomechanics to improve gravimetry. So that's where you would have a levitated superconductor, which could be put into a Schrödinger cat state. So like be split in space. The plus state would be up, the down state would be down, and there would be a relative difference in the gravitational field seen by those two components. And you could then infer that by measurements and have a very sensitive measurement of gravitational fields. And another thing I've been looking at is measuring electromagnetic fields using ensembles of spins, which you might get from using nitrogen vacancy centers in diamond, or using Rydberg states of atoms. So yeah, I think there's a lot of potential here, and certainly it's something that's uniquely quantum. That for these kinds of improvements, you're looking at an improvement from a precision that scales like 1 over the square root of the number of spins you have to 1 over the number of spins.